heap trees, right? What is this heap? We have studied about binary tree initially. Binary tree, it says that no, it kind of a tree structure. Tree, then we evolved to binary tree, then we have evolved to binary search tree. On then we have come up to AVL tree. If you summarize what we have seen here, tree means you can have a root and it can have n number of children like this. There is no limit in the number of children. Binary tree, it says that it should have either 0 child, 1 child or 2 child. So, something like this. Something like this can be a binary tree. Binary search tree, we have imposed an additional property on this binary tree. What was the additional property here? All the elements on the left child of the root should be less than the root element and right side should be greater than the root element. Then on top of BST, we have included something called AVL tree. What is the condition added here for AVL tree? We said that in AVL tree, the difference of the height of left subtree and right subtree should differ at most by 1. It should be a balanced tree. Okay, the balancing factor should be at most 1. The difference between the height of left tree and the right tree should differ by 1. It is an additional condition added on AVL tree, right. On the same line, we are going to have heap tree also. Okay, right. We have seen about tree, binary search tree, AVL tree. Next, we are going to study about heap tree. Okay, I will not say that it is a version of AVL tree. It is kind of AVL tree only, but we have different properties here in heap tree. What is the property here in heap tree? In binary search tree, we said that root, okay, if 7 is the root, left side I can have some elements like this, 4 and 2. If you observe, all the elements on the left hand side are lesser than this root element and all the elements on the right hand side, okay, are greater than the root elements. This is what we said in binary search tree. Heap tree says that the largest element should be at the root, okay, something like this, 14. Then I can have here 7, I can have here 2, I can have here 3, we can have here some maybe 13, 9 and 10. If you see here, the property of heap tree is, you take this node 2, its root should be greater than this 2, okay, this root should be greater than these 2 elements. So, 7 is greater than 2 and 3. Next, here 13 is greater than 9 and 10, then 14 is greater than 7 and 13, like this. Okay. So, the tree should be from, now if you see from bottom to top, the element should be in increasing order. The root should be the largest element. Okay. So, you see left child and right child both are lesser than 14. Again for 7, left child and right child both are less than 7. Okay. This is the property of heap, right. It is not exactly matching with binary search tree. It can be considered as other variation of binary tree. The condition here is that root should be the top largest element. Okay. Its predecessors, its successors, 14, its children, left child and right child should be less than 14. And for 7, its left child and right child should be less than 7. Okay. This is the property of heap tree, right. So, all these BST, AVL tree, heap tree, red black trees, okay, red black trees, we have RBT, we have B tree, we have B plus tree, like this, all are different variations of binary tree concept. Okay. So, but in our syllabus we have to study about binary search tree, AVL tree and heap tree, right. Heap maintains a property. What is the heap property? The root should be the largest element, its child should be lesser than the root. This should be applicable for every node. Okay. Let us dwell deeper into heaps. What is heap? What are the different properties in heap? Okay. So, if we go forward, a heap is a tree with some special properties. Okay. The basic requirement of heap is that the value of a node must be greater than or less than the values of its children. Okay. We have actually, I spoke about one example here by taking 14 this side and 7 here, 13 this side, here also 2 and 3, here some 9 and 12, or maybe you can put some 10 also. This is one kind of a heap. I can have another heap like this, 3, 7, 9, 10, 12, 15, 16. This is also another kind of a heap. Okay. What is the heap property? Heap property says that, right, the value of a node must be greater than or equal to the values of its children. Here you see, the value of this node 14 should be greater than or equal to its children. Yes, it is satisfying. Why? 14 is greater than 7 and 13. Same way, the value of a node 7 should be greater than its both children's. Yes, it is satisfying, it is satisfying. In bracket there is something given here, or less than also. See, it can be less than also. This example, see, the value of a node should be less than both its childs. So, it is satisfying. The value of this node should be less than both its child. Yes, it is less than. So, this is called minimum heap, min heap, and this is called max heap. If you observe one thing, in the max heap, in the whole elements, all the elements of the tree, the largest element is at the root. That is your max heap. If the smallest element is at the root, that is our min heap. Okay. So, the property value of a node must be greater than or less than also than its children. This is called our heap property, right. A heap also has an additional property. What is that additional property? All leaves should be at level h or h minus 1. Okay, like this. If you remember complete binary tree, we have studied 3 different types of binary trees: full binary tree, strict binary tree, and complete binary tree. Okay, right. So, a heap has an additional property that all leaves should be at h or h minus 1, like this. It can be here or here. If you observe now, why we are telling that it should be at h or h minus 1, this is also an AVL tree. This is height balanced tree. Okay, this is also a height balanced tree. That is why when I explained you, we said that BST, from there came AVL tree, from there comes your heap tree. Okay, why when we are saying that all the leaves should be at level h, at same level, like this. All the leaves should be at same level, or they can be at different levels like this, but at most at h or h minus 1, that is allowed, not h minus 2. If there is no this node is not there, this is not a heap tree. Why? Because it is not balanced, no. If you observe, apply the property of AVL tree, this tree 1 with 2 and 4, 5 is not a balanced tree. That is why we say that the additional property is that it indirectly it is satisfying the AVL property as well, right. Heap also has an additional property that all leaves should be at h or h minus 1, like this. Okay, meaning that heap should form a complete binary tree. We studied 3 different types of binary trees: strict binary tree, complete, and full binary tree, right. So, this is complete binary tree is our heap tree. Okay. So, again I will repeat the property of heap: all the elements of a node should be greater than its children. This should be applicable for every node, and the leaf nodes or the child nodes can be at level h or h minus 1. Okay. Let us see different types of heaps, right. So, what are different types of heaps we have? So, first one is min heap, the second one is max heap. What is min heap? The value of a node must be less than or equal to the value of its children. See, 11, it is less than 15, 12, 15, it is less than 16, 17, 12, it is less than 14, 13. So, this is minimum heap. It means the smallest element in the tree is at the root, whereas in max heap the largest element is at the root. It is greater than its children's. See, 15, 6. There is no order of BST. Don't bring BST here. Why? Binary search tree, it says that all the elements in the left hand side should be greater than, less than, that logic is not there here. See, here I have 15, here I have 6, here I can have 10, we can have in any order, there is no order. It's a kind of variation of a binary tree. Okay. So, the root node is the maximum element, this should be greater than its both child elements. So, 15, this should be greater than both its child elements. 6, it is greater than both 4 and 3. This is your max heap and min heap. So, in the whole course we will be talking about max heap. The standard widely used is max heap. Okay. Heap, from now onwards heap it remains max heap only. By default it is max heap. Always the maximum element is at the root, its children are lesser than this root. This is applicable for every node in the tree, right. This is about max heap and min heap. Next we have binary heaps. Okay. Up to 2 children, the rule is every node can have maximum up to 2 children. Binary heap, binary tree logic only, same thing, you see 1, then 2, 3, then 4, 5. So, up to maximum up to 2 children we can have, meaning here heap can have multiple children, whereas binary heap should have only maximum up to 2 children. So, 2 like this, then 2, then only 1, that is possible. Okay. It can have 0, 1 or 2 children, but it should follow the property of heap. One property is it can be either min heap or max heap. Max heap means the root should have the largest element of the whole given set of elements, right. How do you represent a binary tree? Very, very important. How do we represent that? We have seen that binary trees or binary search tree or AVL tree, we are using linked list style of storing, right. We are using linked list. Why? You are creating a node like this, you are putting here data, height, left pointer, right pointer, like this we are trying to store elements in a tree. Okay. But for heap we will be using array representation, because we have to follow some logic here, we have to follow some approach here, right. So, array representation is very useful here instead of linked list implementation. We can still use linked list also, but arrays are much better for heaps, especially binary heap. Okay. How do we store it like this? You see here. So, how do we, you have a tree like this, this is a max heap given to me, I have 17, 13, 6, 1, 4, 2, 5. Using level order traversal, in the order of level order traversal, fill the elements in the array. See, I have 7 nodes, I have created array of 7 with indexing 0, 1, 2 till 6. First I am entering 17, then I am entering 13, then 6, then 1, 4, 2, 5. In sequential order, level order, we are trying to fill the elements in a tree. In this way, we are storing the elements of a tree in a array. We use array representation for playing with binary heaps. Okay. But how do I store this? Storing is okay. How do you store this? Suppose if I have a tree like this, 1, I have 2, I have a left right child here like this, 3, some 4, 5, it has a left child 6, 7. For example, I have this tree, right. How do I store it in the array? What should be my size of the array? Okay. If this element is not there, for example, this is not there, how do I store this kind of trees? Okay. So, that is important, we will try to see that, right. So, we have to first calculate the height, depending on the height you have to create the array size, right. 2 power h minus 1, 2 power h minus 1. This height is 3, therefore, 2 cube minus 1, 7. So, you have to create an array of size 7. Okay. Whether there are elements, 7 elements or not, we are not bothered about it. See, this given tree here, okay, I am having 1, it has 2 children, 2 and 6, 2 is having a left child 3, that is it. But how many levels are there? 3 levels, no? Height h1, height 2, height 3. So, the maximum height of the tree is 3. So, you have to create 7 nodes. It means you have to create array with 7 elements. Okay. How do we fill it? How to fill the elements in this array? You have to follow level order traversal. So, 1 here, 2 here, 6 here, 3 here. Remaining will be empty. The remaining will be empty. This because we don't have left and right child, they will be empty. Okay. Right. Now, given this reverse process, this is very easy, no? I hope you understood how to insert elements into the binary heap. Okay, this is very easy, inserting elements, just do level order traversal, first level, then second level, then third level, fill them as it is into the array. Okay. Now, given a array, suppose you are supposed to find out the tree. How do you find out? For that, we have to know the location of parent and child nodes. Somebody gives an array, what is the tree structure, that we have to find it out. Okay. So, the first very important point here, the first point, the parent node for any element at location I will be I minus 1 by 2. You take an example, take this element 4, what is its index? Let us take something else, take this element 2, what is its index? 5, I value is 5. I want to know who is the parent of 2, I want to know who is the parent of 2. So, what is the index? 5. So, its parent will be at location I minus 1 by 2, that is 5 minus 1 by 2, 4 by 2, 2. At index 2 we have 6. So, 6 is the parent of 2. Okay. For any given node, if you want to know its parent, the logic is if it is at location I, its parent will be at location I minus 1 by 2, I minus 1 by 2. Okay. Now, for any given node at location I, its children will be at 2 into I plus 1, 2 into I plus 2. For any given node I, okay, let us take I want to know the children of 13. Okay, I want to know who all are the children of 13. So, that I is at 13 is at index I equal to 1. Then its left child will be at 2I plus 1, that is 2 into 1 plus 1. At index 3, its right child will be at 2I plus 2, that is 2 into 1 plus 2 at 4. So, elements at 3 and 4 index are the children of 13. Okay. Using this logically, we are going to play with binary this heap trees or binary heap trees. Okay. So, when you have an array structure with you, it means suppose you are inserting a new element, where you have to insert, assume this is not there. Okay, assume this is not there. You want to add a right child for 6. You want to add a right child for 6. So, first find out where is 6. 6 is at index 2. 6 is at index 2. You want to add a right child. The right child logic is 2 into I plus 2, that you put 2 here. 2 into 2 plus 2, that is 6. So, the new element which you are inserting, you have to store it at location 6, that is here. Okay. So, we use this two important principles. If an element is at if an element is at index I, its parent will be at I minus 1 by 2. If an element is at I, its both child will be at 2I plus 1 and 2I plus 2. Okay. Using this only, we are going to play the whole insertion deletion operations on heap trees, right. So, basic structure of heap tree, you have to create an array to store the elements, count to have the number of elements, capacity, because you see I do not know, I may declare a int a of some 10. Okay. So, array of 10 is created, but what if I want to insert more elements into the tree? What if I want to insert more element into the tree? Like this is there, I want to insert, so 7, 8, 9, 10 already over, I want to insert a new element like this or here, right. For that we are maintaining a capacity. Next, heap type, whether heap type is min heap or max heap. Max means 1, min means 0, like this will have some encoding. If the heap type is 1, it is max, if it is 0, it is minimum. It is our own choice, we can do it while implementing that, right. So, we are going to store 4 parameters to have a heap structure. Now, how do you find out maximum element in a heap? Very simple. How do you find out maximum element? Since it is a max heap, we know simply print the root element, that is it. Simply print the root element. But where are we storing the root element? We are storing at in array. So, the element at 0th index contains this largest element. In a max heap concept, the element at the root 0th index, the element at the 0th index of the array contains the maximum element. Okay, right. Heapifying will see this, will see about how to heapify, how to insert and delete an element, okay, into a binary heap. So, if you quickly see the important point here, we use array representation for heaps, and in that parent will be stored at I minus 1 by 2, child will be stored at 2 into I plus 1, 2 into I plus 2, right. So, this is about introduction to basics of heap tree.